So, in this class we will learn about the crystal symmetry. So, basically crystal is have a periodic nature, means lattice points are arranged periodically, orderly. Right, or unit cell are repeated in the space. So, for so this I think so this unit cell are repeated in space in all direction, right. So, what I want to mean that crystal has periodic nature either in terms of lattice point or in terms of unit cell. So, whenever any system have periodic in nature, so it has some symmetry. So, crystal also have symmetry because of this periodic nature. So, there are mainly 4 types of symmetric element or symmetric operation one can apply on crystal. So, symmetric operation basically when you operate on a system, after operation whatever change will occur, whatever change will happens, and then after that operation it will come to its original configuration. So, one cannot distinguish before operation and after operation. So, that is the symmetric operation. So, this mainly 4 types of symmetric operation. Four types of symmetric operation. Are seen in case of crystal structure, means this 4 type it is invariant with respect to these 4 symmetric operation. So, one is translation, second is rotation, third is reflection, and fourth is inversion. So, these 4 types of operation, symmetric operation one can apply on the crystal, and after this operation we can get the invariant position, invariant configuration. So, this translation, you know that as we have discussed that crystal lattice one can generate from using this translational vector this is T equal to what I wrote, I think N L M one can write N A plus M, sorry, L M N. Okay. So, taking all possible value of L M N, one can generate lattice points in space. So, so this lattice point itself is defined that this environment or surroundings of each lattice point is identical. So, from in crystal one lattice point to another lattice point one can go using this translation vector. So, when it will go there, so you will get the same environment. So, whether whether any translation or any shifting from one position to other position of a point, one cannot distinguish. So, it is obvious that crystal have that symmetry, and basically crystal lattice or lattice points are generated using this translation vector. So, it will have this symmetry, is obvious, it is very obvious, but this other rotational reflection inversion, that one can check whether how this crystal shows this this symmetry. So, rotational basically in crystal, if you choose a choose an axis, and with respect to that axis, if this crystal this is rotated. So, after rotation, if you get the same configuration, if you get invariant position configuration, then we will tell that this crystal have rotational symmetry, and that axis will be called axis of rotation. So, this so if I take this say cubic crystal, okay. So, this is the cubic crystal, this unit cell. Eight corner, 8 lattice point. Now, if I choose an axis to the center of the face and perpendicular to the face, is passing through the opposite faces, through the middle point of the faces. Okay. So, now with respect to this axis, if I rotate this crystal, so what will happen? So, just if I draw just 2 dimension, just if I draw this face, let me make it square. Okay. So, this space I have taken, and this is the axis of rotation. Okay. So, it is basically this axis, and this other part is other part is attached with this face, right. So, whenever this face will rotate, so whole things will rotate. So, that way if we imagine, so what will happen with respect to this axis. So, when you will rotate, so see this corner will come here. So, this corner will come here after rotation of 90 degree, Similarly, so it will be, so you cannot, then after this rotation of 90 degree, so it will be invariant. So, whatever the now we are seeing, so after 90 degree rotation with respect to this axis, basically you will have the same configuration. So, one cannot distinguish. So, similarly, after another 90 degree it will come in again in same configuration, and then another 90 degree, then another 90 degree. So, 360 degree. So, complete rotation 360 degree. Now, in this case, in this cubic crystal with respect to this axis, so basically after 90 degree we are getting the invariant position, same configuration. So, n equal to 360 by 90, that is 4. Okay. So, this 4 basically it is called this fourfold axis. So, what does it mean? With respect to this rotation axis, this we can rotate this cube, and with it comes in 4 times in symmetry position, in invariant position. Okay. So, if we know this is fourfold symmetry, it has fourfold symmetry, then what is the angle that you can find out? 360 degree by n. Okay. So, if it is fourfold symmetry, so after 90 degree you will get the symmetry. In case of hexagonal, One, two, three, four, 1, 2, 3, 4, 5. So, then slightly. So, these are hexagonal, we know this hexagonal Bevis lattice, where basically ABC, A and B are same, but C are different, and two angle are same 90 degree with this one, but one angle is 120 degree. Okay. So, if you rotate this crystal with respect to this axis, okay. So, dotted line I am giving because this is perpendicular to the plane. Okay. So, then after 60 degree, this 60, then another 60, then another 60. So, 1, 2, 3, 4, 5, 6. So, it will have 6-fold, this axis will be called 6-fold axis, okay. And that means n equal to 6. So, after each 60 degree rotation you will get the symmetry, you will get the invariant position. Okay. So, so this so this the one has to choose proper rotational axis of rotation, and then with respect to that axis of rotation, what is the how many fold of symmetry exist for that system, that crystal, that one has to find out. Okay. So, in case of cubic crystal, as I so it has rotational symmetry. This crystal has rotational symmetry, not rotational symmetry. It has fourfold symmetry. Okay. So, so degree of symmetry depends on this. If it is just one fold symmetry, means after complete one 360-degree rotation, you will get symmetry. Okay. So, that is obvious, always this happens, most of the case it happens, but it is a two-fold, three-fold, four-fold, this as many number of fold of symmetry are there. So, that are basically it tells that this system are more symmetric, it has higher degree of symmetry. Okay. So, another thing, this is not only the one axis with respect to that crystal have cubic crystal have symmetry, rotational symmetry. So, there are other axes also one has to find out. So, obviously, you can see this through these two surface, another these two surface. If I take the axis, so that also it will be four-folded axis of rotation, four-fold axis of rotation. Similarly, you have this other two faces, these faces and these faces. Okay, these faces, this face and this face. Okay, so through these two faces also, these faces also. Through the middle of these two faces, if you draw the axis, basically you will get the that will be also the similar, that same similar rotational axis having four-fold symmetry. Okay. So, basically for about the axis passing through the center of the face. So, this cubic crystal have three axis of rotation, right, about this axis passing through the center of the faces. So, other axis also possible, say if I take axis with respect to that body diagonal, if I take the axis with respect to body diagonal, so it will have also it will have the rotational symmetry. So, with respect to this axis, if you rotate, so one can see that after 120-degree rotation, it will come to the original configuration. Okay. So, so this is also rotational axis. Now, it has how many fold? This, I think it will have three-fold symmetry. Because n 360 by 120. So, it is n equal to 3. So, you will have three-fold. So, here this is four-fold symmetry, three axis of rotation of four-fold symmetry. Okay. And then you will have this type of axis passing through the diagonal. along the diagonal. So, how many we can have? How many we can have? This 1. So, 1 and then this and this other side, this and this other side, which one? I think this one, okay, these two. Then similarly this and this other side, this and the other side, okay. So, this 4, starting from 4, this diagonally opposite this lattice point, if you connect, so it will be body diagonal, and you will have 4, you will have 4, you will have 4 from this 4 point. So, you will have basically 4 axis of rotation of 3-fold symmetry, right. Similarly, whether any other rotational axis exists or not, one has to find out. Yes, if you take the axis passing through the middle of the edge, these are the edge, 8 edges are there. So, passing through the edge, middle of the edge, opposite edge of the cube. So, opposite edge is this one, and opposite to this one that one. So, through middle, if you take the axis, so you will get the another rotational axis. Now, with this rotational axis, so if you rotate by 90 degree, no, you will not get the same configuration, but if you rotate by 180 degree, so this face will come down and this will come up, but both faces are same. So, you will get invariant position. So, you will have, so it can be treated as a axis of symmetry, rotational axis of symmetry, and it has two-fold symmetry, and you can have this this type of, from this cube, how many you can have. So, through these two edge 1, through this 2 edge 1, okay, and through these 2 edge, this and this opposite this one 3, this and opposite this one 4, this and opposite this one, I think this one 5, and this and opposite this one, so that will be 6. So, you will have 6 axes of rotation, 6 axis of rotation of two-fold symmetry, right, two-fold symmetry. So, rotational symmetry, what is rotational symmetry? It may have manifold symmetry, okay. So, for a particular crystal system, we have to find out the first axis, and with respect to that axis, you have to see the how many fold symmetry are there, okay. So, here just I have taken one example of cubic cell, cubic crystal, and I am trying to find out this in details. Okay. So, I think these are the axis of rotation, and no other axis for this rotational axis for this cubic system. Similarly, reflection also, with respect to reflection, one can see whether the crystal is having symmetry or not. Some crystal may have symmetry, some crystal may not have symmetry. So, with respect to this, So, let me draw a cube. Let me draw a cube. Okay. So, for reflection you need like rotational symmetry, one has to choose axis, a line. For reflection one has to choose plane. So, it is with respect to that plane, that is basically mirror plane, with respect to that plane whether crystal has symmetry or not. Okay. So, if I take a plane, I think this not, if I take a plane, if I take this plane, if I take this plane, so with respect to this plane you can see this half. So, this point will corresponds to this point, right. This point will corresponds to this point, okay. Deflection from this plane. Similarly, you can see this one. So, this half exactly same to the other half. Okay. So, what does it mean? So, I have taken cube and then cube have this type of things, lattice point arrangement. I have taken one mirror plane and I am telling that so this point is equivalent to this point. Okay. So, but to see the symmetry, if I tell the symmetry that cube has this reflection symmetry with respect to this kind of plane. So, from this information itself I can generate this lattice point, I can find out the lattice point, position of the lattice point, position of the atom. Okay. So, that is why this symmetry basically helps to determine the internal structure of the crystal, how atoms are arranged. Okay. Just if one know the symmetry of that crystal, so one can know about the details distribution of the atoms or lattice point in that crystal. Okay. So, that is the importance of the symmetry of the crystal. So, similarly see this, just this plane we have taken this way. No? So, similarly this way also one can choose plane. So, how many planes one can choose this way? So, that will give basically 3 planes of symmetry, this parallel to face, 3 plane, this 3 plane of symmetry, because 2 face giving 1 plane. So, 6 faces are there. So, you can draw this type of 3 planes, right, mirror planes. So, you will have 3 planes of symmetry, and if you take the plane along the diagonal, so this, with respect to this diagonal plane, so this side one half, and this, you see, this reflected one will be the another half, right, reflected one will be another half. Okay. So, this is one plane. Similarly, you can draw this other one plane. Okay. And from here again you can draw this and this. Okay, it is 4. Okay. So, basically opposite faces, from opposite faces you are getting 2. So, 6 faces. So, from each face you will get 2, each parallel faces you will get 2. So, 3 set of parallel faces in cube. So, you will get 6. So, 6 planes, 6 diagonal planes you will see, 6 diagonal plane you will see. So, earlier we have seen 3 and for this diagonal plane this 6, total 9, okay, total 9. So, I will discuss in next class, I will discuss about inversion. So, just remember, so from axis, from rotation we have got 13 axis of rotation symmetry. Here we got 9 plane of symmetry, mirror plane of symmetry. Then rotation, from rotation I can show for this cube it will be just one point at the body center, that is the only inversion point. With respect to that, this cube crystal will have the symmetry. So, that is why this 13, 9, 22 plus this 1. So, cube crystal have 23 symmetry element, these are rotation, axis of rotation, plane and this point, these are called symmetry element. So, cube crystal have 23 symmetry element. Okay. So, I will continue in next class. Thank you.